So C, we have a second object of mass small m, don't get the small m mixed up with capital M, and it's initially at rest and is placed gently onto mass capital M and sticks to it. We now want to know by what factor does the energy of the oscillation change if a mass small m is added when the mass capital M is moving through its position of maximum velocity. Okay, so since we're looking at the factor that the energy changes, we should look at the initial energy, I'll call that EI, and the final energy, EF. And so we want to know what factor changes by comparing the two and just seeing what the difference is. So, and this term by what factor kind of indicates that there will be a common multiplier, so that EF will be some constant multiplied by EI, and that should give us the change. So what do we need to know? The initial energy. Remember, this is moving through the position of maximum velocity, so the initial energy is going to be half mv squared, in fact half capital M v squared, and in fact we'll call that vi squared as well, because the velocity is going to change when you add this on. And then the final, I don't know if we need this, we'll give it a go anyway. The final energy will be half, it's meant to be 2 half big M plus little m, because the mass has changed, you see, and the velocity in this case will be the final velocity squared. So we can see just straight away from that there's a m plus m factor, or plus m anyway, and the final velocity is what we're looking at to see. So how can we work out the final velocity to substitute that in? Particularly, how do we work out the final velocity in terms of the initial velocity? And the best way forward seems to be to use momentum ideas. So I'm going to bring this across over here. If we look at the initial momentum, Pi, that's going to be capital M times by the initial velocity. If we look at the final momentum, Pf, that has to equal the initial momentum, capital M times Vi, but it also equals the final velocity, or m plus m, big M plus little m, times by the final velocity. So those two are equal, which means we can take this section of that equation, since the final equals the initial is how we work that out. That's in case you're wondering. I can't remember if I skipped over that or not. Anyway, we can take this section, rearrange for Vf, and substitute that in, because we've now got m and Vi. So let's just do that. Vf equals m times Vi divided by m plus little m this time. So we've just taken this section and divided both sides by that. So now what we would do is substitute that in. So we'd take this whole part here and substitute it into that part of the equation and see what we get. I can already see that there's an m plus m on the bottom, which might cancel with that m plus m on the top, but remember that's squared. So let's go ahead and do that and see what we come up with for the final energy. EF equals half m plus m, big M plus little m, times by big M Vi divided by big M plus little m, and all of that has been squared. Okay, so easiest cancellation, as what we could see before, is to get rid of one of our m plus m's on the bottom and m plus m on the top. So we can get rid of that. We can then get rid of one of these. We could rewrite this as that squared over that squared, and now we get rid of that square part. So we end up with, let's write that out and see what we end up with. We have half m squared Vi squared over big M plus little m. So that gives us a nice equation which looks very similar to our, I'll just write this EF. That gives us a nice equation which looks very similar to our initial, there we go, we can see the whole thing now, to our initial equation. So our initial equation was half big M VI squared. Now we've got half big M squared VI squared over M plus M. That means that there's a factor in this of big M over M plus M, which if we took out, if we could somehow get rid of that from our equation of the final energy, we would see that it equals exactly the same as the initial energy. So this here is the factor by which that is increased. And that's that question done. So now we need to look at question 2. Question 2 says, by what factor does the energy of oscillation change if a small mass m, or if mass small m, is added, but this time, instead of passing through the center, through the point of maximum velocity in the center, it says when mass m, capital M, is at the position of maximum acceleration. So maximum acceleration is when it's at the extreme range of motion at one or the other end. So max velocity, remember, is there, extreme acceleration is there or there. So what you need to know about that point is the velocity is temporarily zero, so there's no kinetic energy. So kinetic energy equals zero. So all of the energy is totally potential energy. So that means the change in mass will not affect the energy, because the energy is stored on the spring regardless of the mass. So the actual change in energy, let's write it like this, delta E, will be zero. Okay, very important, nice and easy, no calculations necessary. And that's that.